Um, okay, first of all, you should be here, all of you, because if you are in Russia, then you must come to the class, all right? If you are not in Russia, you can't just look at the recordings or Zoom or something, but if you are in Russia, you must come, all right? And it's important for you to come because during the seminar, I will need you to solve problems here together with me, so please come. All right, now, at the end of the course, we will get some grade from 2 to 10, right? Like always. You already know the system here, so I'm not sure right now what kind of system I'm going to use, so how I'm going to compute the final grade. But I will be telling you that next week because it depends on how many of you are here in Russia. Okay, so let's see that. Now we will have, of course, homeworks, assignments, the final test, middle term test, and so on, right? All that information will be given to you next week or something. Okay, the last seminar I think will be on December 17th, okay? And yeah, I think that's it. So look, today we are just going to remember everything that we should know from previous semester, all right? So everything you had to know in your exam. By the way, you are, just give me a sec. Full, like, let me find you here. Yeah, all right. Let me just write here that you came. And no, wait. For Obidare, right? Yeah. Okay. Now, let's start then. So look, so this is a course on probability theory, right? And probability theory, everything in probability theory goes around this triple from here, right? Just a second, I'm new on this thing, yes. And so this triple from here is the main idea, the main thing on probability theory, all right? So if you don't know the meaning of this, you're gonna fail this course, that's for sure. So please be very careful on understanding every single thing here, okay? So let's start with this thing, okay? So this is a set, and the name of this set, this is the sample space, right? This is the sample space. And in this set, we have, this is the set of all elementary outcomes. So we have this set omega here, capital omega here, and we have some elementary outcomes that we call omega, right, also. So this is these are the elementary outcomes, and this is the sample space, right? So we have this set. For example, if we throw a die, then omega for us can be the following. So 1, 2, 3, 4, 5, and 6. So we have the set of all the possible outcomes from this die, right? So we have 6, and we can see that the cardinality of omega is just 6. So this is finite, and that's good, right? So this is discrete probability by now. But of course, omega can be not only finite, but also infinite. It can be countable or uncountable. And last semester, we studied everything related with omega being countable, right? Now, this semester, we will have to study omega being uncountable. For example, the set of all the real numbers or something like that, okay? So we have that this is the sample space, the set of all elementary outcomes. And then we have the sigma algebra, right? So this is a sigma algebra. And sigma algebra is a set of subsets of omega, right? It's a set of subsets of omega. And we know that the definition of the sigma algebra is the following. So we need 3 conditions, right? For a set to be a sigma algebra. Do you remember the conditions? So what's the first condition we need to a set to be a sigma algebra. So the whole space itself, omega, has to be an element of the sigma algebra. The second one is that if A is an element of the sigma algebra, then what? The complement of A is an element of the sigma algebra. And finally, so we have two different kind of definitions here. So for example, if we know that A and B are elements of F, then the union of A and B is also an element of F. This is the definition of an algebra. No? So this is the definition of an algebra, right? So this is an algebra. But here we are not talking just about an algebra. We are talking about the sigma algebra. So what's the difference between an algebra and a sigma algebra? What do we need to change here? So, remember? No?
All the subsets of omega must also be elements
Of omega? No, well, no. I mean, we have to change this, right? So look, here we are talking about just two sets, A and B. And don't forget that the word sigma somehow means infinite, okay? Somehow, for us. Okay, so this, okay, just a sec. Not this one. Oh. So we have to change this. We have to change this to more to some extended. So let's make some extended version of this property here. So if we have some countable collection of events, Bi, which are elements of F, right? So here we have only two. And if we have two, it means that we can have 4, 5, and so on, right? But we are not talking about any infinite sequence of events. And here we talk about an infinite sequence of events. So we have that if we have this countable sequence of events, then we know that the union of all of this also belongs to F, right? So the union, the countable union of these events also is an event, so also belongs to F. Hi, you are late. Like, how many? 15 minutes. Please don't be late, all right? Okay. So we have that. We have the sample space, we have the sigma algebra, and finally we have this. And this is called the probability measure, right? So the probability measure. Okay, and what is this? Well, this is a function from the sample space to the real numbers on 0 and 1, all right? So we have all the elements of capital omega, and we assign some number from 0 to 1, some real number. And this is going to be the probability that this happens, right? And that's it. So this is all that we need. So this is like the very, very, very basics of probability theory, right? You have to know this, that's for sure. Now, and of course, we call this the probability space. So this is the probability space, this triple from here. And if we have this pair, so if we have some set omega and we have a sigma algebra on this set, then we call this a measurable space. All right? So we have all of that, and good. Okay? Now, what else do we need? So we define that, and today let me just repeat that. We're going just to repeat everything that we should know from previous semester, all right? So from the very beginning to the last topic, and the last topic was joint probability distribution of two random variables. Okay, so we have this, good. Then we start with the classical model. The classical model on probability theory, right? So in this case, we have that the sample space is finite, right? So this is the first condition. And for example, we have that the sample space is this one. Okay, so the cardinality of omega is just n, right? So this is the number of elements in omega. And in this case, what do we call a sigma algebra? What can we call a sigma algebra? So there are many different options, right? But what's the obvious one? So what sigma algebra do we use for this case? Again, we are working on a finite sample space. So for example, this one, right? So we have a die here, and the sides of the die, right? And elementary outcomes are just 1, 2, 3, 4, 5, or 6, okay? And here we need to define a sigma algebra. So what sigma algebra can we define for that case? Or for this case, right? So the same. So usually we just take the set of all the subsets, right? The set of all the subsets. And this is possible because this is finite. But this is not always possible, right? So we can do that only in the case when this is finite. Don't forget that. Now we have this, and we say that this is not good. No, I have to change this. All right, doesn't matter. So let's take this A, right? So A is an event. So A is an element of F. So A is an element of the sigma algebra, all right? And how do we find the probability of A? In this case, so we are working on the classical model. How do we find the probability of A? So A is just a subset from omega, right? So A is a subset of omega. For example, I don't know, A is the following event. So we have that the die gives an even number, right? So we just throw a die once, and we look at the number, and this is some event that we can define there. The die gives an even number. So who can tell me what is equal A to? So A. So what? Yes, exactly, right? Well, actually, no, it's much more complicated than that because, wait. But what if, yes, of course, we only are doing once, right? So we have 2, 4, and 6, right? Okay, so, no, this is not true, sorry. This is not true. Why this is not true? It's impossible. Okay, A here. No, it's true. I'm sorry. Yes. What's going here? Okay, this is impossible. 2, 4, and 6. All right. So what's the cardinality of A? 3, right? So how do we find the probability of A? The cardinality of A over the cardinality of the sample space, right? Just like that. So this is the classical model. Okay. So this is the easiest one, and this is the one that we used many times for solving many problems, right? So we have that. And then we got a new model No, not this. Yeah. Okay. So we have a new model, and that's the Bernoulli scheme, right? So could you please tell me what the Bernoulli scheme is? No? Really? Yes, so, again? So we have a coin, right? We have a coin. What do we do with this coin? Flip it, right? So we get success, or 1 or something, and then what?
We flip it until if we want head, then we flip it until we get head, and that is the number of fails, or like the number where we get the full success.
Yeah, so look, we flip this coin n times. We fixed the number of times we flip this coin, n times, right? And we call maybe 1 and 0, success and failure, I don't know, 1 and 0, let's say, all right? And we care about the number of successes that we have, all right? So could you please tell me what is the probability if the number of, so let's define the following event. Event is we got k successes here. So what is the probability of AK? 1 over what?
1 over 2 raised to power k.
Ah, I forgot to tell you. So this, we get success with P and failure with 1 minus P. Why 1 minus P? So again, think, we did this many times. Come on. So, yes, so P to the power of K and 1 minus P, n minus K. And what else? Yeah, n choose K, right? So that's it, right? Okay? Good. And this is the Bernoulli scheme, and this is going to be very useful because we use it for the Bernoulli distribution, right? Okay. What else? Let me see. Now, conditional probability. So we just finished lecture number 1, or no, this is like lecture number 3 or 4, okay? So now what is, so if we talk about conditional probability, right? So this is the probability that something happens if we know that something already happened, or that something, well, actually, maybe it didn't happen, but it could happen. Right? So look, what is the probability of A given B, right? And this is equal to probability of the intersection over the probability of B. Yes? Okay? And using this, we define that 2 events, A and B, are independent if and only if what? So what's the definition of independence of 2 events? Yes, the intersection is, again please?
P of A times P of 2.
Yes, so the product, right? So the probability of the intersection of A and B is equal to the product of A and B. And this is true if A and B are independent, right? And we obtain this from here, okay? From the definition of conditional probability. Okay, good. Now, next, we have that, and using all of this, we can obtain two important formulas. And these are first, the total probability formula and the Bayes formula, right? So, do you remember? So, look, we have omega, right? And we can divide omega and we can express omega as the disjoint union of some events. So B1, B2, and we have here Bn. Okay? So it means that omega is equal to the disjoint union of B1 and Bn, right? So all these sets. And we know that each of these sets from here belongs to the sigma algebra. Now, we want to find, we can change that, yeah. We want to find the probability of A, right? So this A. We want to find the probability of A. And we can express the probability of A as the following sum. So can you tell me? What do you think is it?
Sum of A such that Bi has.
Yeah, so sum of the probability of what? Of A given Bi times Bi. Yes? And from 1 to n. Okay, this is the total probability formula. And using this total probability formula, we can find the Bayes formula. And this one is the following. So what if so here we had A, and we could find A using this partition. By the way, this is called a partition. So this is a partition of omega, right? Now, how can we, so we could find A using this partition, but what if we want to find some of this Bi from here, knowing A, right? So what if we want to find Bn, for example, if we know A? Okay, so using this formula, we can just write this formula here. So we got probability of A here, and here we have the probability of the intersection. Yes? And we can write this from here. So let me just do the following. So we write this over here. So this is the probability of A. And here we are going to write the probability of Bn times the probability of A given Bn, if I think it's correct. Yeah, should be.
So I think it's just A given Bn. There's no B.
You mean there's only this?
Yeah.
No. Yeah, this should be for sure. So don't forget that this is different. Here we have conditional probability, all right? So here we have the intersection, yes? And for finding this, we use this formula again, but we just change everything. So instead of writing here Bn, we write A given Bn, and here the probability of Bn, right? So that's why the probability of Bn and the probability of A given Bn. Yes? Is that clear? And this is the Bayes formula. And that's it. So this is discrete probability. This is like introduction to discrete probability, and this is enough for solving a lot of problems, right? Now, do we have a break? Do you need a break or no? All right, let's continue. Okay. Now, what else can we do here? Okay, independence, right? So we talk about independence of two events here, but this is only for two events. What if we have more than two events? Then there are two different kinds of independence, and we call them how? So the first one, yes, uh-huh. And yes, pairwise, right? Okay, so this is if we have more than two events. So what's the difference? So what's the definition of this one?
All of them are independent of each other.
What do you mean by all of them?
All the events.
Yes, and so if I have, for example, A1, 2, and AN, right? So, and I know that the probability of A1, A2, so the intersection, right? AN is equal to the product Is this the definition? No, it's not. It's almost the definition, but there's something missing. What is missing here? What do you think? This is not enough. So we have n events.
Oh, if you take all the intersections of...
Yes, the intersection of all the subsets, all the possible collections that we can have, right? So here we can change it by like this. The probability of the intersection of all subsets of some set I, right? It's equal to the product over all and AI. Well, I is just 1, 2, and n, right? So, wait, let me check. Here is subset, all right? And here, this is, yeah, well, kind of, no, it doesn't look good. Here, I have to change this by, no, like this, and here like this, and here it's a subset of this set. Okay, so we take all possible subsets of all the numbers from 1 to n, and this has to be true, all right? So all the possible collections that we can have, this equality here has to be true. Now, which one is more general, this one or pairwise independence? So if we know that some collection of events are mutually independent, does it mean that they are pairwise independent? All right, and what about this direction? If they are pairwise independent, does it mean that they are mutually independent? No, right? Because pairwise independent, by definition, is, yeah, so all the possible pairs of events, for all the possible pairs, this equality has to be true, right? Here we have pairs, but not only, okay? That's why mutually independence is more general. Okay, good. Next, what else do we have? Now we have to talk about random variables. Random variables, let me, yeah. Okay, random variables. So, what is a random variable? No, an event is no. A random. No, that's a probability. The probability is just a probability. I mean, the probability of some event is just a number from 0 to 1. That's it.
The possibilities of the probabilities.
No. No, really? Come on, most of you got really good grades. Summer was long, right? Yeah, it's been 3 months. Okay. Anyway. By the way, so you must be 5. Yes, you are all of you here, right? We still have waiting for. Yes, Mihail, he is there on YouTube, and Daniel. And we still have to wait for Monica and I don't remember her name. Yes. All right. Where are they, by the way? They should be there. All right, so a random variable, you cannot forget this, because this is, okay. Look, a random variable xi, I like to call it xi or eta, but if you look at English books or something, they call it like capital X or capital Y, right? But here we call it xi, just like that. So this is a function, okay? So this is a function from the sample space to the set of the real numbers. Okay? So a random variable is not a number. I mean, it's a number because you obtain a number, but it's not a fixed number. It's not, I don't know, blue or yellow or something like that, right? So these kind of things are events or elementary outcomes, right? So don't confuse elementary outcomes with a random variable, okay? A random variable always gives you some number, 5, 10, whatever you want. An elementary outcome can be yellow or can be anything you want, right? But this is a number, okay? So this is a function, like a function, right? Here we have the sample space, and here, well, psi of omega, right? Because here we have omega, something like that, right? So it's a function, okay? Okay, so a random variable is a function. What kind of function is this? So it depends. It depends on this, on omega. If omega is countable, so what if omega is finite or countable? Then xi is just any function, all right? Any function can be a random variable, okay? But this is not true if omega is uncountable. So if omega is uncountable, then this is something that we call a measurable function, and we are going to define that, I think, next class, okay? So again, if omega is finite or countable, then xi is just any function. And we worked with any function previous semester, okay? Good. Now, so we have random variables. And what can we do with random variables? We can define if they are independent each other, right? So we can define that, for example, two random variables xi and eta are independent, and by definition they are independent if what? So, and we write it like this, by the way. So we already know the definition of well, not the same. That's the deal. Where is that? Let me find it over here. Yeah, so here A and B are events. But here we are talking about random variables. So these are different things. So how do I write that psi and eta are independent? Yes. So first we have to define the following. So we have psi and we have to define the set of all the possible outcomes, right? So the set of all the possible outcomes are going to be, I don't know, xi from 1 to, I don't know, from 1 to n. Let's call just n. Let's just don't get. Okay, so I didn't erase the one. N. So this is n kind of, right? So this x, so we have the following, right? x1, x2, and so on. And for each of these possible outcomes, what can I define? I can define the probability that psi equals x1, yes? And I can define the probability that psi equals x2, and so on. And I can do exactly the same for eta. We did this for psi, and we can do exactly the same for eta, yes? So we can define all the set of all the possible outcomes. Yj, right? J1 from 1 to m. Okay? Now, we say that psi and eta are independent if and only if the probability that psi equals x I and eta equals yj is equal to the probability that xi equals xi times the probability that eta equals yj for all possible pairs of I and j. Yes? So there's a difference between events A and B and random variables xi and eta. Okay, don't get confused, because this from here, this is the event A, this is the event B. Okay, and here we have A, and here we have B. So we used that, but it's not the same. To n, just let's just yes, it's possible, countable. Right? Now, so we have random variables, we defined the independence, and what else can we define? So if we have 2 random variables, we can define this kind of independence. But what if we have 3 random variables, right? Or n random variables, so xi1, xi2, and xin. What kind of independence can we define here? Yes, exactly. So the same mutual independence. So they can be dependent mutually or pairwise, right? And we define it like this. I mean, we just change the event for random variable being equal to something. Okay. What's next? What else do we have to define here? So we already have these random variables. What can we find for each of these random variables? What kind of characteristics can we define for these random variables? Which one? Well, yeah, all right, yes. So we can define the probability mass function, right? And what's the probability mass function? Well, before defining that, we have to talk about the probability distribution. Okay, so the probability distribution of a random variable. The probability distribution of psi. So what is that? It's just a function which gives the probability of occurrence of each of the possible outcomes of this random variable, right? So this, in this case, so this is the probability distribution of psi. But the deal here is that since psi, we have different options for psi, right? So this can be here either any function or maybe some weird function that we don't know about it. But if we know that, if we are talking about the discrete case, then we can define the probability mass function. So we describe the probability distribution of psi using the PMF, all right? And the PMF, for example, for this case, the discrete case, is just this table from here, okay? And yeah, and so this is the probability mass function. But if we have continuous random variables, then we don't have any PMF, of course. We have the probability density function, the PDF. The probability density function, we haven't studied this. We don't know what is this right now, but we will, right? And for both of them, we can define the CDF, the cumulative distribution function, which, as far as I remember, we haven't studied also. So we only know the PMF, all right? So we only know the PMF for discrete random variables. Good. So this is new, right, like for this semester. So PMF, and we can define the PMF for different distributions. Now, what distributions do we know? I mean, we many times, like, what's the first one? Bernoulli distribution, right? Which one is this? So we flip a coin once, we have only two outcomes, 0 or 1. So two outcomes, 0 and 1, and we get 1 with probability p and 0 with probability 1 minus p. That's it. This is the Bernoulli distribution. Then we have the binomial distribution. And in this one, what do we describe? So what kind of random variable? So for the binomial we have, so for the Bernoulli we had one coin, just one. Or yeah, we have one coin and we flip this coin just once. And now for the binomial distribution, we are going to flip this coin n times. All right, so we are going to flip this coin n times. And again, we obtain success with probability p and failure with probability 1 minus p. And what we care about is, so in this case, we define the following random variable, psi, just the sum of ones, right? So how many times we got success. And then the PMF of the binomial distribution, so the probability that psi equals k is just equal to, I just did it somewhere. So this is, yeah. So n choose k, p to the k, 1 minus p to the n minus k. Yes? And this is the PMF for the binomial distribution. Good. What else do we have? What other distribution do we know? The Poisson distribution. Good. The Poisson distribution with parameter lambda, right? Now, what kind of experiment do we have here? So again, the binomial is that we are flipping a coin n times. And we have success with probability p, right? And we get the number of successes that we obtain. Now, what if n is very high, right? N tends to infinity, and the probability tends to 0. Then to find this number is impossible, right? Well, it's possible, but actually it's impossible, all right? So we have to use some approximation, and this approximation is the Poisson distribution that we use. So this is the case in which n tends to infinity and p tends to 0. And actually there's a relationship between p and n. So p equals lambda over n. That's why we have to use this lambda here.
So, I don't understand what you mean by p tends to 0.
The probability is very small. The probability that you obtain success is very small. Yeah? Sure? And n is very high. So imagine that you have, I don't know, you have like this area here, and you get success if you pick the point equal to the center of the area. So the probability is very small, right? Something like that. I don't know. And the times that you do that is infinite. So in that case, don't use this one. Just use this one. Okay. Now, so and we have to find the probability that xi equals k. Which is? Huh? Oh, something, right? Okay. I think it's the factorial. Oh, no, k factorial. I don't remember also. E to the minus lambda, and here we have k factorial, and here lambda. Let me see. I just don't remember exactly. It should be lambda to the k. Yeah. Hmm? No. It's quite difficult as far as I know, because these are like different. So this is a file, and this is a different file, and then I mean, I'm going to try. So but I don't have a USB here with me. If you have it, we can try it at the end of the lesson. Yeah, I don't have it also, but you will have the recordings of. So it's okay. So this will be on YouTube, I think. Okay, but it doesn't mean that you don't have to come again. All right. Okay, so we have this, and this is just like finding this limit, right? So this is somehow equal to the limit when n tends to infinity of this, n choose k, p to the k, and 1 minus p to the n minus k. Okay, so if you find this limit and you change p for lambda over n, then you will get this value from here. Okay, now could you please tell me what is equal this? So from the sum from k0 to infinity of lambda to the k over k factorial e to the minus lambda. What do you think? 1, right? Because this is the sum of the probabilities. So this is the sum from k1 to actually 0 to infinity of the probability of xi being equals k. And the sum of all the probabilities is just 1. Okay? Good. Yeah, so we have this Poisson distribution, and we have the final distribution, which we call, which one? There's a fourth one. So this is the third. Another one. No? The geometric distribution, right? The geometric distribution. And do you remember what kind of experiment are we doing here?
Points maybe on the area.
No, that's a different one. You are talking about the geometric model of probability. That's different, all right?
Until we get a success.
Yes, so we flip the same coin. Every time we're flipping coins here, okay? But this time we want to find the probability. So we flip this coin until we get success, okay? That's it. And we want, so, and what do you think is this? The PMF. So we're flipping this coin until we get success. And we want to find the probability that we will get success at the trial K, at the Kth trial. So we need K minus 1 failures and 1 success. So this is equal to yeah. So you don't have to know this by heart. I mean, you just have to know the experiment that we are doing here. If you try to learn this by heart, you will forget it. I mean, I didn't know this one also. Kind of, but all right. So let's see what else do we have here. Okay, so we already defined all the main distributions that we know, and we will know more distributions this semester. We will talk about the exponential distribution. We will talk about the famous normal, or the normal distribution, like the most important one, and you will see why this is so important, right? So like I mean, all of you look something like this, and all of you know that this is somehow the normal distribution. Well, what does it mean? You will know that. You will have to know that. So let's see. Now, let me continue here. Okay. What can we find for each of these distributions? What characteristics can we find for each of these distributions? Yes, the expected value, the variance, and so on. So the expected value of a random variable give us what? Give us a number, right? So we obtain a number. So this is a fixed number, all right? So again, psi is a function, but the expected value of psi is a fixed number. So for example, what is the expected value of the expected value of psi? And we know that the expected value of psi is a number. So what is the expected value of 5? Is 5, right? 5. The expected value of a constant is just the constant itself. And since this is a number, so this is some c, so this is just equal to the expected value of psi, all right? So this is a tricky question I may ask during the test or something, right? So the expected value of something. This is like easy, but if you know the definition, right? So we can define the expected value, and the expected value, by definition, what is that? What does it represent for us? So we have some random variable, right? Psi. The random variable give us, I don't know. Yeah, so the average value of the average outcome of this random variable, right? So we can think about that like this. So we have this function here. This is psi, and we can, so this is psi of omega, right? And we can think about the expected value as a number here. So this is the expected value of psi, and this is the average value of this function somehow, all right? And just like that, okay? So how do we find the expected value of a discrete random variable? So we had defined before this, this. So we had defined psi, and these were the possible outcomes of xi, right? So how do we define the expected value of xi? Well, not how do we define, but how do we compute, because the definition is different. So how do we compute the expected value of xi if we know that xi is defined like this?
Probability that psi is equals to xi, the total sum, times xi divided by n.
You don't have to divide anything. Yes. So this is xi. All right? You just take all the possible values of this random variable xi and you multiply it by the probability that the random variable gives you this outcome, this value. All right? So this is the expected value. This is how we compute the expected value. Okay? Now, let's talk about the properties of the expected value. First, which one?
Expected value of psi equals to expected value of psi.
That's not a property. That's, but actually, I mean, the expected value of a constant is just a constant. So let's say, but that's not a property. That's from the definition. Okay.
Expected value of A psi plus B is A times expected value.
Yes. All right. So the first is that if we have the expected value of A psi plus B eta, right, where A and B are real numbers, then, so this is called linearity of expectation, right? So this is A times the expected value of psi plus B times the expected value of eta. This is the first one, okay? And we prove it. And of course, I'm not going to prove anything right now. If you don't remember the proof or you want to check the proof, you can check the lectures from previous semester, right? So the second one, what else can we say about the expected value? What do you think?
Expected value of A times psi is equals to A times expected value of psi.
Right? But you mean A times psi?
Yes.
But we already did it here. This is this one, right? I mean, you can change this by 0 and you get that. All right, let me just. How this works? No. Oh, all right. So the second one is that, which one? I don't remember also. Let's check. What else can we say about the expected value? Of course. Yes, if we have some function, so let's say that we have some random variable eta, and this is a function of another random variable, right? So psi is a random variable, and a function of a random variable is a random variable because it's a function. Actually, this is hard to prove, and this is something from measure theory, and this is really hard to prove, that if we know that this is a random variable, then this is a random variable as well. This is really hard to prove, but we're not going to do it. But just don't forget about that. It's interesting. So if we have a function of a random variable, then the expected value of eta is what? Well, yeah, you can just put this here, but that gives you what? So you can easily here have from 1 to n, and you can write here phi of xi, right? So because all the possible values of xi are xi, you just apply the function that gives you eta and multiply by the probability that xi equals xi. All right? So You see it? All you have to do is to change this one by the function, by the value of the function, okay? And that's it. Now, and what else do we have for expected value? Yes. And this is a question that I always ask during the exam. I mean, if I don't ask this question, is either you did really good or you did really, really bad. So, but so this is times, right? Like multiply. Is this true or false? Why? I mean, sometimes this is true. Yes, if they are independent. So this is something that I always ask, and don't forget about that, because from here you can get that, for example, if two random variables are independent, then it means that the covariance is 0, right? Or something like that. So this is very important. So if xi and eta are independent, then the product of two random variables is just the product of the expected value of each of them. Okay? Good. Now, that's for the expected value. We have 20 more minutes, right, of the lecture. What else can we? Now we can define the variance of a random variable. How do we define the variance of a random variable? So, what is the definition of the variance? So, what is the meaning? Let's start with that. So, the expected value is the average value, right? What about the variance? Yes, is how far this random variable is from the expected value. So, because we can have two different functions. So this is xi, and it's something like this. And the expected value is here. And we have the expected value of eta, but eta is something like this. And they can be equal, right? So we have two absolutely different random variables, xi and eta, and their expected value is exactly the same. But of course, these two functions are different. So we have to somehow define this distance from here, right? So how far each of these values is from the expected value. Then we have to find xi minus the expected value of xi. So this distance, right? This distance. And yeah, but let me just, and we should find the expected value of this, right? So the expected value of all these distances from here. But this distance, we get here plus, and here we get minus. So if we get this expected value, just like that, we get that this is equal to 0, right? That's why we have to get this square here, right? And so this is the definition of the variance. Now, how do we compute it? How do we compute the variance? I mean, we can compute it like this, but it's not usual. Yes. So how do we? This is equal to what?
Expected value of xi square minus e xi whole square.
Like this, right? Yeah, it should be. So this is the way we compute the variance, okay? Notice that here, the random variable is a square here, so this is a new function, but here we have just the expected value of xi, and everything is square. So if we know the expected value of xi, then we just have to put this number square. But here, if we know the expected value of xi, this is not enough, we have to find something else, right? Good. Now let's talk about the properties of the variance. And now variance of psi plus eta is equal to variance of psi plus variance of eta. True or false? No, false. All right, this is not true. Plus something, right? But this is true in which case? If they are independent, all right? So this is the question that I always ask also. If they are independent, then you can find the variance of the sum of two random variables just like the sum of the variances, all right? If they are independent. If they are not independent, this is not true. You have to plus something else. Huh? Yeah, 2 times the convergence. All right. This is not a property because this is not true. I mean, yeah, this could be a property if just they are independent. Okay. Now, what about the variance of A times psi? A is just a real number. So, A times the variance of psi, A squared, right? Don't forget that, A squared. And you can easily get that from here because we have a square everywhere. So here we have A squared. What else? Yeah. Okay, good. Let me see what else can we.
Variance is always greater than 0 except if the psi is constant function.
Variance is always what?
Greater than 0.
Ah, yes. That is true. This is other property, right? Always is greater or equal than 0 because we have a square. So if you get, I don't know who was it, or maybe from your group or not, but someone get that the property, that the probability of something was equal to 4. So no. I mean, if you do this, I mean, of course you can compute something and you get 4. Clearly something is wrong, right? And if you really can't find the right answer, then just write, for some reason I obtained 4. I don't know why is that true. I mean, but I don't know where is my mistake. Here, look, here are my computations, right? But this is not true, of course. The probability is always between 0 and 1, all right? Always. Now, what else can we say? Yeah, now we can define the covariance. The covariance.
Sir,
Yes.
please, for the variance, could you explain the square part again?
Which one? Where?
Why are we squared? The reason why we're squaring is not in the definition of the formula.
In the definition. Because if we don't, then we get, so if we don't put this square here, then this is going to be equal to 0.
Not always, but sometimes. Even when it's not.
No, always. Can you see that? Look, this is the expected value of this difference. If this is the expected value, and let me, yeah, here, so it means that this is exactly in the middle, somehow, of this function. So it means that exactly the same number of times that you go up, you go down, right? So of course, if you sum up this, and this is plus, and this is minus, then you will get 0, right?
So when we square it,
Minus, you don't,
when we square it, all the parts that are negative become positive and
no, all the parts that are negative have something positive, and then the sum is going to be 0. For example, here I have minus 5. So look, the expected value of eta minus the expected value of eta is equal to minus 5 in this point. And somewhere in other points, the eta minus the expected value of eta is going to be 5. And that's for all the possible values of eta. And then, of course, the sum is going to be 0. Right? That's why we put this square here. Okay? Good. Good. Now we have to talk about the covariance between psi and eta. So we were talking about the variance and the expected value of just one random variable. Now we have to talk about the covariance between two random variables. Now we talk about two different random variables. What is the meaning of the covariance? What does it represent? Yes, this is somehow the measure of independence, right? So the covariance is the measure of independence between these two random variables. And how do we define it? This is the expected value of xi minus the expected value of xi times eta minus the expected value of eta. Yeah, this is by definition, but we compute it using this formula, the expected value of xi eta, right, times eta, minus the expected value of xi times the expected value of eta. Yes? So this is the covariance. And if xi and eta are independent, then it means that the expected value of xi times eta is equal to the expected value of xi times the expected value of eta. Yes? So it means that this is equal to this, so this is 0 in this case, right? So if they are independent, then the covariance of these two random variables is 0. If the covariance is 0, it doesn't mean that they are independent, okay? And we prove it. I gave you some examples about that. So don't forget about that. So if they are independent, then the covariance is 0. But if the covariance is 0, it doesn't mean that they are independent. If the covariance is 0, we call these random variables uncorrelated. All right? So if the covariance between xi and eta is 0, then xi and eta are uncorrelated random variables, right? Yeah. Now, what else? This is somehow the measure of independence, yes? But if we put this some a here, then this value is going to change. I mean, a here and a here, or something like that. So if we multiply these random variables by some constant, then the covariance is going to be different. But these two random variables have the same measure of independence, right? So somehow we need some value that doesn't change if we multiply each of these random variables by some constant. Is this clear? Yeah? Okay. This is important. So we need to add something else here. We need something called the correlation coefficient between xi and eta. All right? And all we gotta do is to find the covariance between xi and eta and divide it by the square root of the variance of xi times the square root of the variance of eta. Now, it doesn't matter if you multiply this by some number or something like that, the correlation coefficient is not going to change. It's going to be the same. And that's really good. And actually, the absolute value of the correlation coefficient between xi and eta is less or equal than 1. And we prove it also. Okay? And here. So, if we have some random variable, if we have two different random variables, we are going to find the correlation coefficient. So this is -1, this is 1, somehow between, so something like this. So some of these values is going to be the correlation coefficient. And as we get closer to 0, then these two random variables are highly independent, okay? And if we get closer to 1 or to -1, then these two random variables are highly dependent on each other. All right? Good. So we are going to solve some exercises now. Nothing new. So you know all of this. So it will be okay. Let me just check. What do we have for today? Okay, yeah. This one? No, first this one. So we have, so this is exercise number 1. So for today, I'm going to solve everything, all right? Next class, you are going to solve it. So I'm going to sit there, I'm going to look at you how you solve the exercise, all right? So I'm going to give you homework. You should all do the homework. So we have 5 people here. It means that I will give you 5 exercises to each of you, okay? And you will just solve them there.
It's on what we did last semester, right?
Yeah, so this is on previous topics that we already know. So the first exercise is the following. So we have n balls, right? Some balls, some n number of balls. And we have m boxes. Okay, and all of these balls are different from each other, all right? So we have n balls, we have the n boxes here. And randomly, we put each of these balls in a box, okay? We have to find the probability that that every box has at least one ball inside, right? So again, we have n boxes, empty boxes, we have n balls, and we somehow put these balls inside the boxes. And we need to find the probability that none of these boxes is empty, right? So that every box has at least one ball inside. How are we going to solve this? We don't know what?
We don't know any relation between n and m.
No, but we can say that, well, I think we should say that n is bigger than. Yeah, so let's say that n is bigger than m, all right? So if it's not, then it's clear. So we know that n is bigger than m. So what do we need to do? How can we solve this? Which one? Pigeonhole? No. It doesn't work here. I mean, no. No, because this is because we are randomly picking the balls. So the position of the balls is not fixed, right? So this is not combinatorics. This is probability, all right? So what do you think? What idea? Something. Think about the boxes, empty boxes.
What I'm thinking is 1 minus probability that one box is empty minus probability that two boxes are empty.
Yeah, something like that. So before going there, let's define the probability space here. So this is the first question that we need to answer, right? So what is going to be the sample space in this case? What is going to be an outcome? There are different ways to do that, right? All right. Which one? So we can get here this tuple of how many elements?
Maximum
N. N elements, yes.
Wouldn't you have 2 raised to power n elements in n?
C is the element of 1, comma m.
Wait, so look, we have a tuple of n elements, n. What does each of these things from here represent? 1 to m, right? So, these are the boxes. These are the balls. So each of the balls got inside into some box, right? So we have, so the length of this is n, right? And these are all the possible values for m. So could you please tell me the cardinality of omega?
M raised to n.
No, wait, m. Like this. So every time we have how many options? M. And we are doing this n times. All right? So that's it. So this is the cardinality of the sample space. Good. Now all we have to do is to find all such possible tuples in which at least such that there is some number from here which is not present here. Yes? So, and these are bad outcomes because it means that some box is empty. Yeah? All right. So let me just see.
So that means we need to expand the set for Li. Because Li might not have a number from 1 to n, right?
Yeah, but we are not going to do it that way. We are going to use the following, what someone suggested before. So the probability that every box has at least one ball inside. So this probability, let's call this A. It's just 1 minus what? At least one box is empty, right? It means that we have to find this probability, right? So let's do the following. Let's call A sub I. This is the following event. Box I is empty. Yes? So what do we need to find? The probability of what? Yes, of the union from 1 to n of 1 to m, right? Of AI. Okay, how do we find this union?
Then minus P of
Yeah, what is the name of that? Yes, inclusion-exclusion formula, right? So, I listen to you. What should I write here?
sum of the singles minus sum of the pairs plus sum of the triples.
Right. So the single minus the sum of the pairs. And here what? The probability of what? Of the intersection. And then plus minus to the what? To the n minus 1, yes, of the probability times the probability of what? The intersection of all of them, yes. So inclusion, exclusion formula, right? Now, what is the probability of A equals to? So this is the probability that box the probability that box I is empty. So what is that? Let's use combinatorics here. How many possible tuples do we have in which the fixed box I is empty? So yeah, so it means n minus 1 to, wait, to the n, you mean? Yeah. Yes, right? So look, we want the box I to be empty. This one. So every time we take a ball, we are going to consider m minus 1 boxes. So m minus 1 times m minus 1 times m minus 1, no, well, n times, right? So this is all the possible ways that I have in which box I is empty, all right? Now, what if I want to find the probability that box I and box J is empty? n minus 2 to the n, right? Yeah, so sorry, I forgot that here. So this is m to the n, and here is m to the n. So all we have to do is to replace that over here. So this is the sum from I1 to m of m minus 1 to the n minus the sum of two different boxes, and the probability is m minus 2 to the n, and so on, right? And here we have, so, and what's the probability of the intersection of all of them? 0, right? So at least one of them is going to have some balls. So this is going to be 0, just 0, right? And we divide all of this by m to the n. Now, let's find the value of this. Yeah, so this is just m. M? Why? Look, here you are choosing the empty box, 1. So from how many boxes do we have? M. You are choosing 1. Right? So m choose 1. M. What about this one?
I'll say the whole formula m times m minus 1 as well.
Well, yeah, so m here choose 2, and so on. So finally we get, let me see. So m times I, right? And m minus I to the n, and this is the sum from I1 to n, to m, sorry, over m to the n. And all we have to do is to write this over here, here, right? So this is going to be here. And of course, you can get some expression, like a more beautiful expression for this, but this is the answer, all right? So is everything clear now? Yeah? No?
I mean, the way you simplified it is not yet clear.
How I simplified it, you mean? Well,
You can write this sum is equal to m choose 1. The left side part.
why this is true? Or
Yes, and also why m choose 1.
because here we are, so this is a sum from 1 to m. But actually here we are choosing one box, the box which is going to be empty. So how many ways do I have to choose one box among m boxes? M choose 1. So m ways, right? And here I have 2 empty boxes. So I have to choose the 2 empty boxes among the m boxes. So m choose 2, and so on. And that's the answer, all right? Now it's clear? Good. Now, a new one. Exercise number 2. So by the way, Daniel and Mikhail, are you listening? Yeah, Daniel is listening. Do you have any questions? I believe that you are trying to, and Mikhail is trying to talk, right? Yeah, I cannot hear you, so for some reason, I think that I should hear you. All right, but anyway, you're listening, good. Okay, exercise number 2. I have a rectangle, and this is of side 2 and 1. You are still writing, right? I can wait for some seconds if you want. Very good? Okay. So we have this rectangle, okay? Well, this should be some rectangle, and we have this side is of length 1 and this side is of length 2. And we pick, we choose randomly a point A, here, inside this rectangle, okay? And now I have to find the following. So the first question here, so question number 1, is what's the probability that the distance from our so the probability that the distance between A and the nearest diagonal is less or equal than x. All right, so I have, let me just do this again. I think it's important. Yeah. Okay, so here is 1, and here I have 2. And I have some, the diagonals are this one. So this is the first one, well, just one diagonal, and this is the other one. Okay? And I have some point A. I randomly chose this point. Okay? So what kind of model am I using here? I'm using the geometric model. So it means that the probability, so if this is the square and this is half of the rectangle, the probability that A is here is 1/2, right? So we know this. And this is the way that how we are choosing this point A. Now, for any value x, I have to find the probability that the distance between A, between A and the nearest diagonal, so this one, in this case, this distance, is less or equal than some x. All right? So x is just any number. And we have to find this probability for different values of x. Now let's start with the following. So how can I choose different color? Here, yes. So look, let's say that this is x. Right? So this distance from here is x, and this distance somehow is x as well, right? And this is x, and this is x. Okay, and I have to find the probability that A is on this area. Is inside this area. Yes? So if A is inside this area, then it means that the distance between A and the diagonal is less than x. All right? For example, if I have it, I don't know, here, A then is less than x. If it's here, then it's not. Okay? Good. Now, I think everything is clear by now. Now, let's think about x. So, what if x is, so before that, so what's the length of the diagonal here? So the length of this diagonal. How much? Yes, so let's say that okay, the length of diagonal is the square root of 5. Okay, so this is the square root of 5. Good. So what if x equals the square root of 5? What's going to be this probability? The probability is going to be 1. No, wait, yeah. Because, of course, there's no way that you can put some point here such that the distance is is greater than the square root of 5, because the greater distance here is the diagonal, right? So if x is the square root of 5, then this probability is just 1. Yeah, so if x is, I don't know, 10, then the probability is 1, because x is too big. So first of all, let's find for which x, so if, of course, if we make the x bigger and bigger, in some point, this point from here is going to come to this point, right? And then for any value greater than this x, for which this point comes to this point, the probability is going to be 1. Okay, so let's find this x. To do that, we need to find, what do we need to find to do that? How do we find this value of x? So look.
Such that probability is 1. The minimum x such that the probability is 1.
Yes. So do you understand why it should be an x such that this thing gets here, right? This is clear, right? Okay, good. So look, let's do the following. Let's find the length of this segment here. How do we do that? So before that, let's find the length of this segment here. And to do that, we can use this angle from here, alpha, all right? So what do we know about alpha? What is the sinus, the sine of alpha? What do you think? You have to guess this one, the sine of alpha. Again, please? So this is alpha, this angle from here. What is the sine of this angle? Huh?
1/2. 1/2.
No. Come on, you have to do it by yourself. Think. What do you know from here? You know this.
Both of them are equal, so it should be 45.
For,
Because that side is also equal. That side is also over.
yeah, but this is not 45. This is not some square or something.
So what is the length of this blue line?
Blue?
Yes.
The length? Yes. Well, I don't know. I mean, we don't know that. Because it depends on x, right? So it can be any value depending on x.
So our answer can also depend on x, right?
The sine? No. So what's the difference between this angle from here, alpha, and this one? They're the same, right? So what's the sine of this angle?
1 over root 5.
Right? Yeah. Now what else? Let's find this beta from here. What is the sine of this? Well, wait. Do we need the sine of this angle? Maybe we do. Yes, we do need it. So what is the sine of this one? We just did it. Huh? Yes. Yes? 2 over the root of 5. The opposite, yeah. How is the name? Catet. I don't. Huh? Hypotenuse, right. But and the name of this is? The opposite side, let's say. All right, you got it. I just don't remember. Okay, so we have the sign of alpha and beta. Good. So it means that we can find this. Let me do it with this color. We can find the length of this segment from here. How? So we can get some triangle here. X, exactly. So the sine, again, the sine of alpha is x, right? Divided by this side. Let's call it, I don't know, A. No, A is the point. Let's call it B. Yes? And, no, wait. What am I doing? Is this? Yes, of course. So it means that this side B, we call B, is just x over the sine of alpha, and the sine of alpha we know that is this 1 over the square root of 5, so this is the square root of 5 times x. So the length of this thing here is x times the square root of 5. Yep. Now, what is the length of this thing here, then?
2 minus 2x.
Yes. So the length of that is going to be just 2 minus 2 times the square root of 5 times x. Okay? And now we can, in the same way, we can find the length of this side. Yeah? Because we know, so we can find the length of this thing here. So let's find it. So we know that the sine of beta is 2 over the square root of 5, but also is x over this, right? Let's call it c. So we obtain that c is just the square root of 5 over 2 and x, right? So it means that the length of this is what? Yeah, 1 minus 2 times. So it means that, well, it's a square root. Yeah?
Sir, please could you show us how you got sine beta? Sir, so show me how you got sine beta.
Because we know the opposite side, so 2, and we know the hypotenuse, which is the square root of 5.
Yeah, so which angle is that better than true equal to?
This one. But this one and this one are the same, because these lines are parallel, right? So they are the same. So we know all of that, and if we have all that information, what can we do? So how can we find this? Wait, first of all, so we wanted to find x such that we get here. So how do we do that if we know this and this? we want to find such x that this intersection here gets here, so here, right, like this. So it means that using this, how do we find this x?
This number
Must be 1.
greater than 0.
Must be 0, right? Because the length here is 0. Yes? So this is 0. Okay? So we find that x is equal to, okay, minus 2, and then minus 2 square root of 5, yeah. So this is just 1 over the square root of 5, if I'm not mistaken. So this is the x. So what does it mean? That for any x greater than 1 over the square root of 5, this probability is going to be 1. Yeah? So for, let me write that here, for x greater or equal than 1 over the square root of 5, the probability of we call this, how do we call this? Okay, let's call this, I don't know, d. The probability of d is going to be 1. Why? Because A always is going to be, so this area is going to be all of this. So all the rectangle, right? So it doesn't matter where A is here, it's going to be less than x. Yeah? All right. Now, we found that, and give me just a second. Yeah, and now, how do we find this probability for x less than, so for x less than 1 over the square root of 5, how do we find this probability? Who can tell me the answer? Who tells me the answer right now get half a point in the final test, in the final exam. What is the probability of this? So what's the solution to the problem? So we already have everything we need.
So 1 minus 2.
You can just tell me the idea if you want. You don't have to compute it.
Just subtract the area of the 4 triangles from the rectangle.
Yeah.
Divide by the rectangle.
Yeah, that's it. So you got your coffee, right? Okay, you got the half point. Am I right? Okay, I will write it later. All right. So yeah, so please repeat again because I think they didn't hear you. So how do you find this probability?
Okay, so this probability is the shaded area in green, which is the area of the rectangle minus the 4 empty triangles.
Yes, right? So we have to find the area of each of these rectangles. Okay. The area of this rectangle plus the area of this rectangle, this one, and this one. And this over 2, which is the area of the rectangle. And we get the probability that we need. Do you understand why? Yeah, because 2 is the area of the rectangle, right? 2, 1. So the area. So that's it. Okay? I think that every seminar I'm going to do that with the half point. It helps. Okay, good. Now let's move to the next one. So the next one is the following. We have the same rectangle, but now we want to find the probability that that this point is, yeah, we want to find the probability that this point A is at a distance less than x from every side. Okay, let me write that somehow. So the probability that the distance between A and every side is less or equal than x. So how do we compute that? So first of all, let's find some x for which this is always 1. For which x this is always 1. Let me just draw this again. So we have here 2, we have here 1.
So the question is to find probability that A is less than x from all sides.
Yes. Right? So for example, if we have A here, then this distance, this one, and this one, they all have to be less than x. Right. So for which x, we know that the probability is 1.
X is greater than 1.
Yes, for x greater than 1, the probability is going to be 1, of course, because it doesn't matter. So the side of the rectangle is 1. So the distance from here to here is always going to be less than 1, right?
So is the answer 2 minus 2x times 1 minus 2x divided by 2?
I don't know. Let's see. I don't remember. Let me see. Again.
2 minus 2x times 1 minus 2x, everything divided by 2.
It seems that it's 2 minus 2x.
Times 1 minus 2x.
No, well, almost, but there's something wrong. I don't. Well, let's see how. Yeah, it's better if you do it.
My idea was so this is x, this is also x, then the distance from here to here is also x.
Yeah, I can say. Well, wait. First of all, don't worry about this distance. So look, you have to worry about this side. Okay, just do it and let's see.
Yeah, so anyway, x here, x, x. So my idea was that A can be in any of these places here because the distance will obviously be less than x. And from here to here is 2 minus 2x. From here.
Yeah, wait, I'm going to stop you. You are doing it for x less than 1. So don't do it, don't do this. Just take care about this. Right? So what's your answer? If you,
X less than 1. Oh, then it would just be these two places
Yes.
x can be in.
Uh-huh.
So
So this
2,
just over 2.
yes,
So this area.
it can be in any area. Okay.
So
We subtract it from the total area because
yes. So no, yeah, but the total. Yeah, I didn't.
2 minus 2x.
Yeah, but what's that? So you have but I did a different. X is less than. Wait. If x is greater than 1, then
I think x is greater than 1 is a wrong.
yeah. I got confused there. So look.
Greater than 2. I mean, greater than or equal to 2 for it to be 1.
Yes, because from here the distance can be yes. So yeah, so your idea is correct, but I did a mistake here. So this should be greater than 2.
So the answer is 3 minus x times 3 minus 2x divided by 2.
Yeah, I don't know. I got confused here. So wait, x less.
Oh, that's it, I think.
Yeah, here. Well, it doesn't matter. I think it's not. So let's check. All right. I don't know where is my mistake and your mistake. Just a minute. So. You can sit if. Yeah. All right. So first of all, you are right about this. Of course, it's 2 here. Yeah, it's 2 because if A is here, then this distance can be greater than 1, of course, but it's not going to be greater than 2. So for x being greater than 2, the probability of D, let's call it D again, is just 1. All right. Now, what if x is less than 1? In that case, D is this event, all right? The event, so the probability that we are looking for, right? So if x is greater than 2, then the probability is 1.
How? If x is greater than 2, it means the point is outside.
No, means that the point is, the distance from the point to every side is less than 2. That is true. That is why the probability is 1. So this is always true. Right? So look, A here, this distance, all the distances are less than 2 always. So the probability is 1. Now, what if x is less than 1? The probability is going to be 0. Why? Because even if we are here at in the center, this is 1 and this is 1, right? So the probability, so the distance is not going to be less than 1 never. It's going to be at least 1. Right? So we can actually, maybe this is less or equal. Yeah, it doesn't matter because the probability of getting to this point here is 0. So if we move here, then this side is going to be 1, I don't know, 0.2, and this is going to be 0.8. So, so always some side is going to be greater than 1. So it means that if x is less than 1, the probability of D is 0. Okay? And now we have to find the case when x is between 1 and 2. Let me erase that. One and 2. So what I was trying to say here is that since x is greater than 1, then we don't have to care about this distance from here to here and to here, because x is greater than 1, right? So this is okay. But if we are here for, this is 1 and this is 2, right? So we got here, let me write, like 0, 1, and 2, like the coordinates, all right? So we are talking about x greater than 1. So x is going to be somewhere here. So this x, right? And this x from here, right? But this x can be also from here. So, and here we have x. So if we have this point here, A, then the distance from A to this side is greater than x, right? So this point doesn't work for us. So it has to be on this region. But if the point is here, A, then the distance from here to this side is also greater than x, because x is here. So the point has to be on this side. So the area that we care about is this area from here. X has to be, A, the point A has to be here, on this side. So this area. Right? And the area, this area is equal to what? Well, here we have 1 minus, so this is x, this is 2 minus x, and this is 2 minus x, right? So we have here x minus 2 minus x. Yes? Wait, so this is the base, and the height is 1, so multiply by 1, right? So this is the area that we're looking for, and over the area.
So you have to subtract 2 minus x
Twice? Why? Wait, yeah. Sorry. We are looking for the, no, wait, yeah. So the length of this is x minus 2 minus x. Yeah? Okay. And this is over 2. So this is the answer. All right? Yeah? I hope it's okay. Okay, good. Now, let's continue. So is everything clear by now? It should be. I really hope it is. Now let's do something else. What can we do? This one already. This one I don't know which. So do you want a difficult one or?
Is it geometric model?
No, just one with this model. So let's finish with something different. So this is an exercise that you had for your assignment, I think. So this is on random graphs, right? So do you remember what a random graph is? You didn't like it? Really? This is, I work on this. This is my research topic. So this is nice, actually. So you look. This is very interesting, and this is really cool because this is one of the applications of probability theory. One of, probability theory is, you have to study probability theory right now everywhere. If you want to study computer science like you do, or you want to study physics, or you want to study theoretical physics or applied physics or anything related to science, you have to study probability theory, all right? And random graph is just one of the many applications of probability theory. And from random graph, that you will have to study random graph, I think, maybe in other courses, maybe, I don't know. Yeah, I think you should have random graph in other courses, that's for sure. No?
Oh yeah, but we did do this stuff about connections due to probability, like this graph, the nodes are connected due to this probability, but
Not probability, maybe how many edges.
Yeah, that's a bit different.
can you remember the name of
You mean the threshold, like how many vertices or how many edges do we need at least if we want this graph to be connected or something like that?
No, that one is combinatorics in complex networks.
Well, complex network, that's, yeah.
Complete something
No,
like
there was this thing that there will be two nodes,
Uh-huh.
and there will be a probability that a node has this edge.
Yeah, that's random graph. Yeah, for sure. All right, look. So a random graph is a random graph. So it's a graph that we obtain randomly. So there are many different ways to obtain this graph, right? So you can, for example, so this topic was born like 50 years ago because of Erdos. Do you know who is Erdos?
Yeah, that was the algorithm. That was the algorithm we did in complex networks.
Yeah, so Erdos, there are many theorems called Erdos something because he has like I don't know, a lot of them. So he created this topic, and originally you have like all the possible graphs, and you can take uniformly, you can randomly take any graph, and this is the graph that you are going to get, right? So this is one way of obtaining a random graph, just like taking a graph from a box, right? But like we did here is that we have all the vertices here, right? N vertices, and we draw an edge between every pair of vertices with probability P, right? So we take all the possible pairs. How many pairs do we have? N choose 2, right? So we take all the possible pairs, and we flip a coin, and with probability 1, with probability P, we get an edge here. At the end, when we already throw this, flip this coin and choose 2 times, we get some graph, right? And this is the random graph, all right? And along the way, we can get, for example, triangles, right? And we already actually computed the expected value. So let xi be the number of triangles in GMP. So GMP is a graph with n vertices, and the probability of an edge is p. Okay? So, and we want to compute, we want to know something about this random variable. So this is a random variable. So this is a number. And we want to know the expected value of xi, right? Yeah, is everything closed? Thank you. So we want to know the expected value of xi. How do we find the expected value of xi? Could you please remind me? Yeah. So the average numbers of triangles that we have. So for doing that, if xi is the number of triangles, let's take all the possible triples, like this one. So 3 vertices, right? How many possible triples do I have? N choose 3, right? So it means that let's take this triple and create a new random variable, an indicator random variable, psi 1, for example. So let's say that this is the triple number 1. And this random variable is 1 if this triple, so if we have a triangle, and if 0 if we don't, right? So 1 is 0, 1 if we have a triangle, 0 if we don't. So it means that psi, we can express it as the sum of all the possible triples here. Yes? Now, how do we find the expected value of psi? So all we have to do is to replace here by this sum here. And what do we know about the expected value? So what's the first property that we studied today about the expected value? What? Yeah, that wasn't a property. Yeah, the sum. This is not a property. Oh, all right, this is something kind of. You mean it? Or what? Yeah, but still, all right. So, so this is the sum of the expected value of psi I from I to 1, from 1 to choose, and choose 3, right? And what is the expected value of psi I? So what's, if we have 3 vertices, what's the expected value? Yeah, that y squared. We have 3. A triangle. Yes. Right, so this is p cube. Is it clear why this is p cube? For everyone. Yeah. So how many values do psi I have? Has 1 and 0. So 1, so this is equal to 1 times the probability that we have a triangle plus 0, the probability times the probability that we don't have a triangle here. So this is 0, and this is 1 times the probability that we have a triangle. And we have a triangle if we have 3 edges there, so p cubed, right? So this is p cubed. So this is 1, so just n choose 3 times p cubed. This is the expected value. Now, and that's what you had to do on your assignment. Only 2 of you did it, I don't remember who. Now we have to find the variance of psi. And by definition, we know that the variance of psi is equal to what? So again, so the formula to compute it? Expected value of psi squared minus expected value of psi and all of this square, right? So we know this. This is just n choose 3 p cubed. So that's okay. We know that, but we don't know this. Let's compute it. So the expected value of psi squared. This is just the expected value of all of this that we have here squared. So psi 1 plus psi 2 plus psi n choose 3 squared, right? And what is this? So how can we distribute the sum here? We can put together all psi being equal. So the sum from for all I 1 from 1 to n choose 3 of psi I squared, right? So yes, plus, well, let's write it like this. When they are different, psi I times psi j. All right? So, so the expected value here, right? So it is clear? Yeah? So we are taking all the indicator random variables here, which are the same. So look, we are multiplying this by itself. So xi1, and here we have xi1 plus xi2, and here plus xi2. So xi1 times xi1, right, plus xi2 times xi2, and all of this is here, right? And when they are different, then they are here. Now, let's compute this part. So by linearity of expectation, we know that this is just the sum of the expected value. So the sum from 1 to n choose 3 of the expected value of xi I squared. Now, what is the expected value of xi I squared? So xi I means that we have a triangle on some triple, right? So this is equal to the expected value to, sorry, so by definition this is equal just to the sum. Now let's write just like this. So what are the possible values? What are the possible values for xi I squared? Yeah, 1 and 0, so they don't change. Then we have to multiply 1 times the probability of what? That xi I equals 1 plus 0 times something, right? So this is just, this thing is just the expected value of xi I. So the expected value of xi I squared is equal to the expected value of xi I, right? Because we are working with indicator random variable, all right? So we have n choose 3 here. Sorry, we have, yeah, n choose 3 p squared. So this is just the expected value of xi. And now we have to find this part. When we have, so here we had the same triple of vertices. And here we have different triples, different triangles actually. So what options do we have? We have 3 options. So this is the first option. Right, we have 2 triangles here. This is the second option. Exactly, with a common vertex. And the third one is when we have 2 common vertices. Right? So we have 3 options here. And these are all the possible pairs of different triangles that I can get. Now all I have to do is to find how many of them do I have. So the probability here, so for this one, how many of these do I have? No, look, first. How many triangles can I have in n vertices? N choose 3, right? So this is for the first one. I have the first triangle. Now I have to choose the second triangle, a different one. How many options do I have? N minus 3, choose 3. That's it. And I have to multiply this by p to the power 6 because I have 6 edges. Right? Now here, I choose the first one, then what? N minus 3, right? Choose 2. Exactly. And what else? 2? Well, yeah, so p to the 5. And what else do I have to do here? What can I change? This vertex, right? So this vertex. So how many options do I have? 3. Right? And for this one, again, n choose 3, then n minus 3 choose what? 1. And multiply by what? By 3 again. I have 3 sides. And this is p to the, how many? 5. 4? 5. Huh? 5. That's it. So this sum is this plus this plus this.
So for the last one, you can change those two. Is it 4 choose 2 instead of 3?
4 choose 2? No, I have 3 sides. 1, 2, and 3. I have to choose the side. No? So this is like the new vertex. New, sorry. And I have to choose the side which I'm going to use.
I was thinking of choosing the 2 vertices we're going to use instead. And shouldn't we get the same answer by doing that?
Well, it should be 3 choose 2. Right?
For the old 3 vertices, not for the...
Yeah. And is it 3? So am I right? 3 factorial, 2 factorial. Yeah, right? And that's it. So this is equal to the expected value of xi. So this is equal to the expected value of xi plus all of this minus all of this. All right? And this is the solution. This is what you had to do. So, any questions?
Oh, we should square that one, right? The one.
This is square? Why? This is cube. Or, square? Yeah, so this is square, yeah. All right? So, that's it for today. I will send you homework. I think I will send you to each of you a different homework. Please do it. Solve it. Yeah, one problem. Yeah, so don't worry. I don't have much time to find all this. All right, so see you next week.